Hello, I'm Shadow of Shadow Gaming, bringing you episode 10 of Programming with Shadow. Today we're going to do a little bit more of arrays. Last time we looked at arrays a little more in depth and we looked at a linear search. So the idea of a linear search is you look at each value in the array and you use that to find the one you're looking for. Today we're going to look at another one called binary search. Binary search works a little differently, as we will see. The idea is that you take a list of numbers. Yes. Okay, let's say we're looking for bad. Let me four. Say we're looking for 4. So in a binary search, you start at the middle, which this one has middle, so you decide. So start here. So we say, is this the number we're looking for? Not. And we would try to throw away one side or the other, but where they're not sorted, that's hard to do. Copy this line just a second. Let's do a sorted numbers. As you can see, I already have a bigger one for us to test here. I'll sort this real quick. So we have a 1. 2's already sorted. 5. 4 here. 5. 6 and 9. No, 6. There we go. Now we've sorted. So now let's say we're looking for, let's say 4 again, but this is going to be a very terrible look. So 4. Start at the middle and we found it. Very not interesting. Let's try again. Say we're looking for 6. We start at 4. Right? So 4 is not it. So from binary search, we can discard 4 and everything below it. In an array, we can't really do that, but we can consider where we're looking. Now let's start again. So now let's start in the middle of this one. So we're looking for 6, and here we go. We found it in 6 tries. Or 2 tries. So that's a binary search. So if we were doing a linear search, we would have searched this one, and then this one, and then this one, and finally 6. So that's where it comes in handy. So if you're doing a lot, or looking through a list of numbers with a lot of searches, sometimes you can save yourself a lot of time by doing this. But for a computer, searching through a list this size, or even there's 100 values in this list here. Even searching through that's not going to take a computer any time. Let's just do a little sample here to prove that. So let's do for int I equals, let's call it index, equals 0, I less than array large dot length, numbers large, that's what we call it. Numbers large dot length. Can't spell. Index plus plus, and index, dot index. So here, say we're looking for, I don't know. Let's look for a light one. Let's say we're looking for 36. So it's 3 from the end. But let's assume we don't know that. So let's say we're looking for 36. So if, let's do this. Let's do value equals numbers large at I. If value equals 36, we print console.write line found 36. And we're done. Don't break out of the loop. Else console.write line, do dollar value was not 36. So there we go. So now this is about worst case. So we're gonna go. I need to get rid of the I does not exist. Should have just used I. Index. Normally I'm an advocate for using good variable names. But in in the case of a loop variable like this, I is the more familiar, even as you can see, I'm even. So here we got a whole bunch of numbers not found, and then suddenly 36. So that was about worst case. So let's say we're looking for 92. So 92. 92, 92, 92. This one's going to be almost best case. Now when we run it, we're going to see that there's only a handful of ones. There we go. The linear search can be nice, but we can do better. So in that. So on average, what you're going to have to do is you're going to, in the worst case possible, you're going to have to search through everything in the array. Maybe you find that the number you're looking for is not even there. That's going to be the same thing here, and if you had a really big number, it would be the same case. So when you sorted it, though, you can do a lot better. Let's do that. This is called a binary search. Let's do. I'm going to do it in a separate. The one thing we're going to need to do first, though, is sort the array. So there's an actual, like you can do. Let's install the C# extension. I've avoided doing this so far, but I think we've come far enough along. Let's do this so I get a IntelliSense, since I'm not typing too well today. Let's look for C# dev kit. It probably recommended it to you. Go ahead and grab it, and it'll take it a moment. I may have to re-log. And it's from Microsoft. And I personally like the old one better, but I understand why they're doing it. If you have the old one, I would stick with it. If you have none, or I wouldn't worry about it. We'll worry about this later. I'm mostly interested in. See, now it's taking forever to background here. While it's doing that, let's go ahead and do initialize. Maybe this was a waste of time. I'm gonna go look it up in the background. I'll find it real quick. Array sort. So you pass it in the array. So numbers large. I think that's all I need. Yeah, that's all I need. So, I don't think it returns anything. So let's see. So then if we do a for I equals 0, I less than numbers large dot length plus console dot line numbers large. Now we should see this in order. Let's see if we do. Now let's try that. Or print each number. There we go. And if you look through this list, it should be sorted. So there's the real way to do this, and that's how I would recommend you do the do your array sorts. We're gonna do it manually here first though. Just know that if you're really doing it, there's probably a C# method already built in. There we go. There's what I was trying to get. So here it's telling me what it does. Let's do a local function. We'll call this call it bubble sort, because that's what the sort we're running. Let's do static. We'll keep our static methods. fixing int array. I bet that's telling me it's not used. Declared but never. So that means that this here's probably finished. Done. Yeah. So now I have the C# dev kit. So now it's telling me some information, telling me this can be simplified. Actually, let's see what that does, because I think the simplification actually collection. So this is the old style, and I think I probably mentioned the new, but as you can tell, I'm not used to using the new. You can do it just like that though, and I personally like that better. I just not used to it. But yeah, so it'll give you a little bit more hints, and we're gonna start using that now. Hopefully, close it. So it'll give you a little bit of hints though on things like the different colors. If there were that white dots like you've seen up here, it's an information. If they're underlined like this, it's warning. So it's telling me it's used. The warning this number. It's telling me it's declared but never used. Go for further. Red will give you an error, something wrong. You can use that to do it a little quicker feedback. Let's do a bubble sort. So the idea of a bubble sort is you take the numbers and let's see. You're taking the numbers and you're swapping them around so that either the largest or smallest end up on one side or the other. What I'm going to do is going to do the largest, find the largest each time and bump it up. Do it like that. So first go and find the 9 and switch 9 and 6. Next one and find the next largest number, which is 6, and switch it with that one, and so forth. Let's do that. So if we think about that, we would do something like 4 or int. I'm going to use I because if I use index, I'm just going to keep creating r.length. Let's do minus. So I have to count your the last squares where you're going to put something basically. It'd be like -1. Let's see what happens. I might be wrong on that. It might be one less than that. J0. So here's the important bit though. The 1 minus I. So the I there is telling it where we're in the array to look at. Now let's just do our swap. So if the array at j oh wait a minute, I'm doing the wrong. This is bubble sort. This is it just clicked as I was writing this. Like, is this what I want to do? Wait a minute. The one I did was a different sort. So bubble sort's going to take each one and swap them. So we'll start here and say one of these is larger, and if two's large or first one's larger, it'll swap them, and it'll do that in here, and that's what it's doing. So it's each one it goes pick one and swap. So I had bubble sort wrong. So sorry about that. I'm thinking of maybe insertion, selection sort. So I did 5 and 2. Okay, 5's larger, so swap their position. 5 and 9. Okay, 9, they're already all right. Skip. 9 and 1. 9's larger, so swap their position. I messed that up. Let's copy this. Do this. So here's the algorithm, as I'm pretty sure. So in the first swap, it does 2 comma copy. So first swap, it checks these two. They're good. 5. So next, 5, 9, they're good. Next, 9, 1. Next, 9, 4. You can see 9 sort of bubbling up to the top or the end, whichever way you want to think about it. 6, 9. There we go. There's one digit sorted. Now we only have to consider the ones less than that. So now we do 2 and 5, they're good. 1 and 5's not. Glad I didn't do a bigger array. 4, 5. And then 5 and 6 are already good, so we're done. Then we go again. Now, 2's 1, 2. And 2, 4, 5, 6, so we're good. We'll do again. 1 and 2. 1 and 2 is alright. 2 and 4 is alright. Good. We'll do it one last time, so 1 and 2 and 2 are already alright, so we're good again. That's bubble sort, so it's sort of bubbling up. Like I said, I think I was thinking of a selection sort when I described it first. This is what I want to do, is this. So if the current value is bigger than the next value, we want to swap them. So we learned about swap last time. The algorithm we're going to use is int temp equals r at j. R at j gets r at j plus 1. R at j plus 1 equals temp. So there we go. There's our little swap function. If we really want to, we can make an actual function. Let's do static. Let's not do static, so let's just do void swap. There we go. We have a little swap method. There we go. There's just a hint. Use tuple to swap values. So that's information here, and here if you want to look into that, you can. I'm not going to do it here, but it's basically another way to swap values. It's a little cleaner, but we're going to use this one because it's tried and true, and you'll see it in other language. However, there is a better way. You can press that tip if you want to see what the better way is. But yeah, so here's just a bubble sort, and I think this does exactly what we want. So let's try it. Let's do a console dot right line. Let's do number. Let's do string dot join space equals numbers. Just like that. We'll do that again here. Let that a return here. However, in the middle, let's do number. Let's do bubble sort numbers. Now let's see what happens. There, if you hover over it, now that we have the extension, you can see telling you information about it, and we'll see later where we can make that even better. Get rid of the int. Good. So what I'm expecting to see is an unsorted array and then a sorted array. There we go. And we can do that with the bigger one as well if we wanted to. Like we can do large. There we go. Well, very unreadable, but if you look at the second one, it's in order while the first one is not. There we go, bubble sort, and you can see that took almost no time. That's just because the computer's fast. This is actually a really inefficient sorting algorithm. But now that we have a sorted array, drop my sorted numbers here. Now we know how to do it. Let's do a new method. static full binary search. Let's do an int. We'll learn a new pattern that sometimes used. Here. Doesn't it like? Oh. We'll worry about that in a second. Let's start. So binary search, we need to consider some edges. We need to consider the right side of the list and the left side, right and left. Start and end's another way to think about it, whichever way you want. I'm going to do right and left first. I've seen it both ways. So right. So start's easy. It's just the start of the array. Right's decently easy as well. R.length -1. There we go. Now let's do while left is greater than or equal to right. So this is our condition. So while there's still more of the array, basically, if they're equal or left's bigger. Now I guess if they're just left's bigger, there's nothing left. Basically, it's saying that the index on one side's or on the other side, and at that point we know there's a problem. So first we need to get the midpoint. So let's do int mid equals left plus right minus left divided by 2. So what do we do there? Take the left, add it to right minus left. So right should be bigger. So let's say it's 10, left 0. So 0 plus 10 divided by 2 equals 5. That's like half the array. So now let's say it's 5. So the next half. So left would be 1. No, left would be 0. Left should update, right? No, it should update. So yeah. Either way, this is going to get us to midpoint. If it's a 5, we get 5. And we have 10 minus 5, which is 5 divided by 2, and then that's 2.5. However, with division, down, I think it goes down. We could check that to make sure, but I think it would go. But either way, we're now able to find a midpoint, and that's useful because now we can say, okay, I start here. If they're sorted, start here, then they're sorted, and I'm looking for 4. I know I don't need to consider anything larger than this, so I don't need to consider this part anymore. Focus my attention. That's what we want to do. So let's do if array at mid. So we have 3 conditions. Equals value. We're done. Return mid. So what we're returning is the index, so where the binary search is. If it's less than the value, let's see, we want to modify the left side. So if this is less than what we're looking for, so we want to say, okay, so take the left and set it to this value. So to take mid plus 1, I guess. So left equals mid plus 1. Other side, else. Let's not do right equals mid minus 1. So it's basically, it says for right, same thing. Okay, we know it's this value is bigger than what we're looking for, so we say right, take this point and subtract 1. Right is now this. I think that's all we need to do. We need to do we do need to do one more thing. So if we never return, that means that it wasn't found. So here's the other thing you might occasionally see. Sometimes, like for an array method like this, you'll get a -1 back. That means it wasn't found or operation failed or something. So here we're saying if we get through this while loop and we never hit return mid, that means we never hit the array or the value we're looking. Let's do binary search. Number is large. So let's look for 33. I'm just going to pick some random values. So 33, 50, 51. Let's do a 39 or 49 as well. 49. So there is a auto assumption here. I'm assuming, or like I said, I'm returning the index. So I guess negative numbers don't matter. So yeah, never mind. Let's look up some smaller numbers here. So -1, 0, 1. I should do more printing here, but I'm not going to. I'm going to say this is all right for what we're doing. So 9 and 100 and 101. So we should see these are pretty uninteresting. It should be whatever the value is, it should be where they are. I think they might be shifted up 1. There's no 0 in my array here, actually. Yeah, no 0. They'll be shifted up 1 for index, but let's see what happens. Here, where we made a mistake. Couldn't find 1, couldn't find 0, or -1, 0. Everything else is shifted down 1 until we get the 101, which was also not found. Yeah, so I'm pretty sure that worked as we expected. That's a binary search. So let's compare these two. So let's do a static int linear search int array int value. Okay, so for a linear search again, we'll just do int I equals 0, I less than array.len plus if array at I equals value, return I, return -1. Okay. So there, as you can see, it's a little easier to do the linear search here. That's easy. We'll just loop through and check if it's there, and if it is, we're done. Binary search, we have to do a sort first, then we have to do a binary search, so it's a little more complex. However, the binary search is more efficient in the long run. Looking up something here, but do that. So how I'm duplicating this, I'm doing Control-C on a line and then Control-V to paste it in the same line. Let's switch every other one. Let's do the first one as search. So here we're not going to see anything interesting at first. If I run this, nothing interesting happens. It just duplicates all the answers. So there, we're search for the searches are working. However, make some make some. Let's add some console.write lines. We're probably going to want to switch to the other array actually. Console.write line checking array at I versus value. All right. Down here, let's do checking array at mid versus value. There we go. Is that the message? Just did this. Checking this versus this. What we're going to look at is the number of comparisons here. This is going to be interesting. Yeah, and way too unreadable. Yeah, let's just do the last. Let's do the first case here first. All these out. So Control K, Control C. Just do one of these. So here, we had to do a lot of checks on the linear search. So it checked 1, 2, all the way down to the very end of the array and couldn't find it, so it had to return nothing. This one, on the other hand, looked at 49 and then 24, 11, and then 5, and then 2, and then 0, and at that point there was nothing left of the array. We can see that's a much smaller number of checks. We do another one. Let's do one here. Okay, Control C, Control K, Control U. This is the best case for linear search. So linear search is going to way outperform binary search in this case. Although I've got a bug. Oh no, I don't. I do not need these. Oh, let's just remove these two. Here, this is best case for linear search. So 1, 1. There, linear search easily beat out the binary search. You can see it found the index. So wait a minute. Yeah, here I'm checking the array at value, and here I'm checking this. So let me fix my comparison. Just so they're the same. So that linear search is checking value, other one was checking index. So now they're both checking value. So there we go, and we can see their linear search way outperformed. Look at best case for binary search, which is 50. Here, we should see binary search easily outperform. So there, one of them had to do 50 checks, the other did 1. There's best case. One more case. Look at this one, so 49. So here, we're going to see binary search way outperform it again. So even though it's a bad case for binary search, it's still better than linear search. Let's cheat just a little, pick one more good value. Let's do 75. This is a great case for the binary search again. So there we go. So this one had to check 75 values, the check 2. So that's the case for binary searches that usually it's going to do better. If it's around, some things you can do if you're doing a linear search and you know it's sorted, do this, but sometimes it's hard to do that with. And say you have a list that you know is sorted, but you don't know what values are in it, you're just going to have to search through them all while binary search you can do a much smaller. We're going to break into a little math just a second, but happening with binary search is so the linear search we could have to check up to 100 values. Binary search, that number's a little smaller. So let's say we have 100. So where is ln n log? That's going to be base 10. 100 log. I used to know how to adjust that, but I actually don't see how to adjust this right at the moment. I wanted to make that base 2 instead of base 10. Yeah, there's some way to do that with the Microsoft's calculator, I think. They've changed it. I actually don't see it right at the moment, though, but basically it's a logarithm. So, done those in math, you know that they make it's basically orders of magnitude it has. So in 100 cases, so it would be log base 2. So that's because it's binary. So each time you throw away half of the options, so it's binary. So log base here, 2 of 10 or 2 of 100. What I should get, if I could figure out how to use this, I was trying to Google how to use this. What I should get is about 6.5, 6 point something, 6.6. Yeah, we'll say 6.6. That says we should be able to find the value of anything in this array in 6.5 checks, so 7 checks. If we look here at the worst case for binary search, 2, 3, 4, 5, 6, 7. So as bad as we can possibly do, let's move this because I don't know how to use it. So in as bad a condition as we can possibly do, it should only take us 7 checks for this. While on the other one in the worst case is 100. That's a lot of difference. If we make it 1,000, or you get 1,000 checks. If you do the binary search, however, it only jumps up to 10. You can find any value of in 1,000, and that's really nice. The what we're talking about is something called complexity analysis. So what you can say is you can look at how fast the function grows. If you've ever done any function, you remember function or done function math, or it's how fast it grows based on your input. So your input size is small, or a linear function value is going to be small. Well, it gets bigger, the number gets bigger. So the terminology you might hear is big O of n. Well, that means that it's linear. You add 10 numbers, it should take 10 times as long to search through, or could take as long to search in worst case. Binary search is logarithmic time. The big O of ln. Log n. It's log base 2, so because we're binary. No, not a major difference. So that means as you get bigger, it's only increasing by the base 2 log of n. That can be really efficient. Like here, as we've seen here, it's almost instant to get these. We haven't looked into making binary or random numbers or anything. But if we did this bigger and did random numbers and did it of say 1 billion values, what you're going to find is, first of all, we won't be able to actually do the print because it'll take so long to print. But what I'm going to find out is that binary search gets it done really quickly, while the linear search is much more slow in that case. So Binary search, if it was looking through a billion, should be able to do it in about 30 attempts or less. So thousands 10, millions 20, billions about 30. That can be really powerful really quickly. Let's see. So let's look at one more thing. So you can sort of see this intuitively if you think about it, because each time you're going through, you're throwing away half the list on each check. So it's reducing how much you have to check each time. This when you're having to search through everything, so you're having to go linearly, you have to go through everything. Look at the bubble sort. I'm going to cut to the chase. It is big O of n squared. So what's happening? The worst case, which bubble sort's almost always the worst case, you have to go through the entire list at least twice. So that's the idea of n squared, growing exponential. Can't think of the word. It's growing at an increased rate. At an increased rate, you're having to go through it at least twice. I want to say quadratic, but I feel like that's not. I'll think of it in 30 minutes probably. So that's a whole field in computer science, that was complexity analysis and algorithm analysis, and that's the part of it I personally always liked, but a lot of times it's hard to grasp and see the importance. And where it comes in is when you get into really large numbers, like say you're doing something a billion times, that's when you might need to pay a little more attention than if you're doing it 5 times, 10 times. So there, we got us a little program. Do one more thing. Do one more. Let's do one more static method here. We've still got a little times while. Let's do a static void display array. Let's make this a little cleaner. Array. We're just going to do string.join. Alright, there we go. There's just our print method. We'll remove these out. Let's do got a little more time. Let's make our driver. Let's see. Let's take in do a pull. It's running equals true. While is running. We're going to just do a little menu here. We're not going to do any checks on the values they give us. We're just do it for now. So let's do console.write line. Array operation menu. On display. So let's do. This was my original thought for the day, but I got off on the other topic, so we looked at the values rather than making the list here. But here's what I was wanting to do. Hit the wrong button. Number binary search. Sort the array. Here's one more thing. Binary search does not work if it's not sorted. we can do console.write. Select an option. So as we've seen before, we should check this, but I'm not going to. Console.read line or empty. Let's do a switch. Switching on. Misspelled. Y'all misspelled something. So case 1, case 2, 3, 4, 5. Default. Break. There's just a case statement. The one's easy. One we just want to display array is large. So case 2 was search for linear search. Okay. Console.write to enter number to find search for equals parse console.readLine. Worry about that. Yeah. Again, I'm running out of time, so I'm just going to do this as is. Numbers large. Search for console.write line to. Let's see. I did a ternary here. I don't remember if I've explained ternary, but we'll look at it real quick. So here, let's say if index equal or is greater than or equal to 0, then we want to do found at index else value not found. So that's a ternary operator. If I haven't mentioned it, you have a condition, and this tells it it's an if. So if true, do this. Else, do what's behind the colon. So there's a ternary. If you haven't seen that, I think I mentioned that, but it's been a while. Case 3 is very similar. So we're doing linear. We're doing binary search instead. Binary search. That feels wrong. Wait a minute. I don't think I knew that, actually. I usually declare my variables outside of the switch, so I actually don't know that I knew that if you declared it in one, it worked in the other. I'll try that. My example actually does it up here up ahead of time. That's interesting, though. So here, let's do double sort large numbers. So the right line array is sorted. And here, exit running is running equals false. There we go. And in this case, console.write line valid option. Try again. let's see this run. So this was what I was originally going to do. I was going to make a menu and just fill out the options, but I decided to go about it the other direction. So one, we can display the array. There we go. It's a giant array. I should add a array. Colon, not a comma. Let's do a 5. Let's try that again and rerun it. There's our array. And linear search, let's look for 92. And at index 1. Oh, I picked a real good value. I didn't even look at the array. I just picked a random one. May have been from when we picked it earlier. Binary search must be sorted. So here we're going to get something weird. There, value not found, although we know it is. And that's because it's not sorted. Let's sort the array. Now let's do it, and let's find 8. There, it found it at index 7, which makes sense. Invalid try. So yeah, so there's us a little very, very, very quick menu. So that's going to be all. I'm not sure if the menu was a good idea or not. I sort of liked where I was before doing the menu. Like I just rushed through a menu really quickly, just do a menu. Got some warnings that I would like to address. What these, you can do the null coalescing like I did before and say search for -1. Since I know that values are always positive in this case. That seems like a search and it's fine. There we go, we addressed the warnings. Yeah, that's basically what I wanted to cover. Give us a start on complexity analysis, look at some a little more advanced algorithms, look at a sorting, we'll probably look in the future at more sorting algorithms. Right now, this is a very simple one. See that this was very simple. You just literally loop through and just slowly bubble your values up to the top. So let's go ahead and conclude them. I think that's everything I wanted to cover. Looking through my little sample program here, I think I actually covered more than I had in my sample program. So let's talk. So in the day's lesson, we looked a little more in depth in arrays. Program here, we wrote a little menu. So we set a is running through. We got our arrays declared up here. I had these generated before we. So we have a is running true while it is running. Print the options. We have different options for different things. Get the user's choice. Again, we should do some cleanup here. That's what I've done here. I don't check if it's a number. I just say if it isn't a number, we give an error and keep going, which is probably all right actually. We have the different options: display array, linear search to binary search, sort the array, exit, and the default. The display we've already seen. I'm doing a console.writeline, and then I'm joining the string to the array. So I'm joining the array's values together with commas and spaces in between. Looks like this. Then we looked at linear search, and we did linear search last lesson. So on it, you just say, okay, here's the list. I'll just search every value in the list till I find what I want, and when I do, I just return that index, and we're done. If I don't find it, I return -1. Nice and easy. Binary search, little more code, but we've seen that it's a lot more efficient to actually look and how it's looking. Binary search, you start with the left and right, and left's at 0, right's at the very end of the array. Then we get the midpoint. So if it's midpoint equals our value, we're done. Else, get rid of everything everything above the midpoint. Here we get rid of everything other way around. Here we get rid of everything below the midpoint. Here we get rid of everything above the midpoint. In doing that, we only have to search through much less of the array than in linear most of the time. There's no guarantees. Linear can get lucky and you can find the first value. Binary can be lucky and you're looking for the midpoint, but you can run into both cases, and sometimes it makes more sense to do one or the other. I've actually seen one really good case for a binary search where linear search was really, really slow, but it just depends on what you're doing. Also did our first stab at a sorting algorithm. This is bubble sort. The idea is that you take a value and you swapping values. So if one of these is larger than the other, you keep swapping. Like here, the first one, this swap, and you swap 92 up until it finds one it can't do, and you keep doing that until you get it. What ends up happening is everything gets sorted up, and you slowly count your numbers down, and eventually you have a sorted list. We also looked at our swap function again. You can see it. We also added our first extensions. First extensions, I did C# dev kit, and it included C#. That may be the one I actually wanted instead of dev kit, actually. It included C# and the .NET install tool. That gives you little hints. You can tell if you've done something wrong. See there, if something doesn't exist. There it's telling me it's declared but never used. Another nice one there, capture or variables captured array and J. That's telling you that since I didn't use static, it's using the values from outside of its scope here. That's array and J, the two it uses. We look here at this one, it doesn't say that, and that's because it's static, so it only knows what's being passed in. It only knows it only knows its world, what's passed in, what's read out. Yeah, that's pretty much where we got to. Mentioned very, very briefly complexity analysis. We'll look at that in the future, but for now, that's something you can look up if you're more interested. Find it a really interesting topic and may look into it more in depth later. Yeah. The one takeaway I have is I need to learn Windows Calculator. It seems to not have the. You used to be able to change it to do a base to. I thought maybe I'm misremembering, but I thought you could. I could not see a button to do that on when I pulled it up. So I might go check that out and see if I'm remembering right. Oh, one other thing. I generated this. One thing we can start looking into soon is here. But I used the library function random here to generate those numbers. I just wrote a little program here to just generate the array lists. Oh, there we go. Yeah, and it just does something like that. It generates it and prints it out for me nice, so I could just copy and paste it to where I wanted it. I did have to make a change. I forgot to add other commas. I should have added those. But that's something we can look at in the future as well, as how to start doing a little bit more of this. Because the next topic we're going to look at is object-oriented programming. So, the idea of object-oriented programming is that everything's an object. We'll learn a lot about what that actually means in upcoming lessons. For C# itself, it's the multi-paradigm language, meaning you can do object-oriented. You can do what we're doing here is called procedural or procedural code. You can also do functional, and everything is a little bit in it. To me, C# really is an object-oriented, or that's where the biggest focus was, and The others here are more of coming about now, while C Sharp's basics was object oriented. So we're going to start looking into that on the next lesson. That will get us to where we're ready to talk about using methods. And we've seen in the pop-up here, it said this was a random class. It's random. We're going to learn how to do some more of this kind of thing. I think it'll be a good time. That'll have to be for next time because we are out of time. So thanks for watching and have a wonderful day.